Welcome back. Today we're going to be talking about the subatomic particles, the pieces that make up the atom. We're going to get an introduction to neutrons, protons, and electrons. And hopefully we're going to be able to see how they each have their own role to play in coming up with the properties of atoms and their elements. Okay, so recapping back from last time. So what is an atom? An atom, of course, is that submicroscopic particle. It's a nanomolecular size, and it constitutes the fundamental building blocks that make up pretty much all matter on Earth. And it is the smallest identifiable unit of any element. And once again, we're talking about the number of protons being the identifier for determining what element you have. Okay, so let's re-meet our three players here, the three subatomic particles. We have protons and neutrons are going to exist, once again, inside the nucleus. And we have electrons that are going to be whizzing around outside, consisting of most of the volume for our particular atom. So protons and neutrons, as they both exist in the nucleus, also both consist of almost the entirety of the mass of the atom. You can see here that protons are designated as roughly 1 atomic mass unit, as well as a neutron. They're both about equally massive. But if you look at the corresponding weight of an electron, it's this number 5.485 times 10 to the minus 4. And so if we were to convert this into non-scientific notation, this would be 0.0005 atomic mass units. So this weighs about half of 1% of a proton or a neutron. So we basically say electrons are almost massless. A common analogy is that they are like flying gnats around your head. Your head has mass, but the electron is just kind of like this buzzing little gnat. On the other hand, although protons and neutrons, which exist in the nucleus, have almost all the mass, the electron still consists of most of the volume. So what does the electron bring to the game? Well, the electron has charge. And so the electron is typically given a -1 charge, and it is attracted, just as opposite charges attract, to the +1 charge of the proton, which exists in the nucleus. So what's holding the electron from just flying off away from the nucleus is that positive-negative attraction that's going on between the electron and the proton. Now the neutron has mass, but it is neutral, and so it has no charge, and so we give it a 0 charge. It just simply adds mass to the nucleus. The interesting kind of another analogy to the atoms and most of matter is actually empty space is that if a proton had the mass of a baseball, right, an electron would be the mass of a grain of rice. So when we think about our atom here and a picture in our mind of the atom, it has this really dense core to it, this dense nucleus that is bringing all of the mass, and it has this kind of very massless but negatively charged that's kind of flying around surrounding it. Okay, so let's go through the subatomic particles one by one and talk about them in a little bit more detail. So once again, the proton exists inside the nucleus, the center of each atom. The proton is a positively charged subatomic particle. It's attracted to the electron, and it has mass. And once again, the proton is the defining unit for what element you have. So if you are a helium atom on Venus, if you're a helium atom on Mars, if you're a helium atom in a kid's balloon, every one of those helium atoms has a nucleus that will contain 2 protons. Conversely, if you are a carbon deposit of dead dinosaurs that are slowly turning into oil, and you're in the bottom of the Marianas Trench, you have 6 protons, and if you are a carbon nucleus in a graphite pencil, also made out of carbon, you're going to have 6 protons. And so we can denote this special relationship between the number of protons and the identity of the element by atomic number, also given by Z. As simply the shorthand notation. The number of protons is your atomic number, and that's Z. Okay, so it's pretty clear that the proton has some level of importance when it comes to at least defining what element you have. It may not be as clear what the significance of the neutron is. Well, the neutron, as I said before, exists in the nucleus, and it has mass, so it provides mass to the atom. But the interesting thing that differentiates at least the neutron from the proton is that, unlike the proton, the number of neutrons in a particular element can vary. Okay, and so when we look at an example like boron, boron always has 5 protons. This is in fact what makes boron boron. If an atom had 6 protons, it would be carbon. If it had 7, it would be nitrogen. So the fact that this particular element, or this particular atom has 5, it means that it is in fact boron. However, there are 2 different types of boron on the planet Earth. There's one type of boron that has 6 neutrons, and one that has 5 neutrons. And because neutrons and protons are basically the entire mass of an atom, you can add up the number of protons and the number of neutrons, and that should get you the mass of that particular atom. And because boron has 2 different flavors, it has an atom that has 6 neutrons and one that has 5 neutrons, we need some way to talk about them, and so what we're going to do is we're going to call them isotopes. So an isotope, and we will talk about more about this later, an isotope is basically an element that has varying amounts of neutrons. Now on Earth, boron that has 6 neutrons and 5 protons, or we say 6 plus 5, 11, boron 11, is about 80% abundant. So if you go to any particular borax mine or any particular store and you buy some boron, which you can do, about 80% of the atoms in that particular borax mine deposit should have 6 neutrons. You alternatively can have 5 neutrons and 5 protons. So 5 and 5 is 10. So boron 10 is about 20% abundant on Earth. Okay, so let's develop a shorthand notation as a way to describe all this information that we're talking about. Some way in which we don't have to simply write out, 5 protons, 6 neutrons. And one of the ways we can do that is via atomic symbols. And so an atomic symbol tells us a lot of information. For one thing, we typically have shorthand for an element, 1 or 2 letters. And then above and to the left of that, we're going to have the mass number. And that mass number, of course, is the combination, summing up the 2 massive subatomic particles, the protons and the neutrons, together. And that's going to give us a number. And then below it, we're going to have the atomic number, and the atomic number gives us the number of protons. And so we can figure out, of course, how many neutrons we have simply by some quick arithmetic. If we know the number of protons and we have the mass number, then we can do simply a simple subtraction, and that gives us how many neutrons our element has. So to give you 2 examples, we have titanium-48 and titanium-50. These are 2 isotopes of titanium that are found on planet Earth, and titanium-48 has 22 protons, and titanium-50 also has 22 protons. Why? Well, because to be titanium means you have 22 protons. But titanium-48 has 22 protons and 26 neutrons. And 26 plus 22 is 48. That's the total mass of this compound, of this atom. And titanium-50 has got 22 protons and 28 neutrons and so in its nucleus. And so we add those up and we sum them to get 50. Okay, so let's do a quick example of this. So on planet Earth, we have 3 different flavors of neon. Neon is an element that, among other things, we will put it into glass tubing or plastic tubing. We pass electricity through it, and the electrons will emit different light depending upon filters and whatnot, and we can make these kind of cool signs. And so in these 3 flavors of neon, all 3 of them are going to have 10 protons, because that is simply what makes neon neon. It has 10 protons in its core, its nucleus. But you can quickly see that the 3 flavors have varying amounts of neutrons. So one type of neon has 10 neutrons, one type has 11, one type has 12. So we're getting increasingly more massive in our atom as we go down. And so to simply get our mass number, we're going to add up our 2 massive subatomic particles, and we're going to get our type of neon. So neon 20, neon 21, neon 22. And we, in all cases, have a percent natural abundance. So this is what people have determined on our planet, the ratios we have of these particular isotopes. So we seem to have most of neon 20 here, about 90%. Okay, so with protons and neutrons, they're fairly easy to describe. We can kind of imagine them. They're these solid packed particles in the middle of an atom in the nucleus. However, electrons, the 3rd subatomic particle, and to the chemist one of the most important of the 3 of the subatomic particles, electrons are the hardest to describe physically, mostly because they are moving so quickly that it's actually it's challenging to describe them as physical particles. They kind of transcend that, and they begin to look like waves of light. And a great example might be that if you can imagine yourself, you're sitting on an overpass and you're taking photos of cars moving on a highway. If you put the delay time on your camera so that it's taking pictures at a slow rate and slow speed, or at least it's developing at a slow speed, you'll see that the taillights be streaking like this. And this is a good approximation for an observer trying to see or trying to imagine what an electron looks like as it's moving around the nucleus. However, for our intents and purposes, because of simplicity's sake, for drawing, we are going to simply denote them as kind of these negatively charged particles that are kind of floating out into space, perhaps even orbiting the center nucleus of protons and neutrons. So once again, electrons, they surround the nucleus, and the number of electrons that exist around an atom gives you the charge of the atom. Okay, and so you can gain and you can lose electrons freely, and that's part of the chemistry we're going to talk about. About a lot of chemical reactions occur by gaining or losing electrons. If there's no charge on a particular atom, then you're going to assume that the atom is neutral or neutrally charged. However, if an atom is going to be getting more electrons, or if it's going to be losing electrons, then we begin to call it something else, and so we're going to start calling them ions. If an atom has a positive charge, we're going to call it a cation, and if it has a negative charge, then it's an anion. Okay, so let's practice this this idea about gaining and losing electrons. And so here's a chemical reaction. Lithium going to lithium plus, and 1 electron. And the question might be what is formed, how many protons, how many electrons. And so let's start off with just lithium here, the parent compound. And we might ask ourselves, well, how many protons are in the neutral lithium species? And if we look here, this is taken from the periodic table, which we'll talk about more. This particular element has 3 protons. And if it has 3 positively charged protons, to make this a neutral molecule, then we need to have 3 of the exact opposite. So we should have 3 electrons existing. And this, as I said, is neutral. However, if we are going to go and we are going to lose one electron, so now we are going to form lithium plus, and we're going to eject an electron, give it away. Then the question might be, what is formed, how many protons, and how many electrons? And so, first off, how many protons does this lithium plus atom have? Well, if it's still lithium, and that really never changes, then we should have 3 protons. Then the question becomes, how many electrons? Okay, well, we lost 1 electron. We started with 3, and 1 of them left, and so now we should have 2 electrons. And so if we kind of think about this, we think about charges, that this particular lithium atom has 3 positive charges and 2 negative charges. So if we add those together, we should have a net positive 1 charge. And we're going to call this a lithium cation. Okay, so let's try the accompanying problem below with fluorine. And so this is fluorine is accepting an electron and becoming F minus, which is fluoride. So fluorine, kind of right here, fluorine has 9 protons, and that means that in its neutral state it should have 9 counteracting negative electrons. And if we're going to give it an extra electron, then we're going to get this F minus. And if we kind of count up what we have here, once again, it's still fluorine, so we should expect to see 9 protons. And now 9 plus 1, we should have 10 electrons. And if we kind of look at what we have here, we have 10 negative and 9 positive, and that should give us our negative 1 here. And this is our anion. Okay, so let's kind of take this to the next level, and let's do some practice here. Whether with given just a little bit of information, whether we can figure out a lot of information about these particular elements. So let's complete this table, and let's assume in this particular case that all the atoms are neutral. So if we look at this top row here, we can see we have 6 protons, 7 neutrons, and this is a carbon atom. Carbon has 6 protons. And if this is neutral, that means that our protons and our electrons must be the same number, because the positive and negative must cancel. So that means that this one must be a 6. And then if we're looking at atomic number should be equal to the number of protons that you have. And so in this case, we look over here, and we should also have 6. Finally, our mass number, once again, electrons don't really contribute to the mass, and so we're talking about protons plus our neutrons, everything in the nucleus, and this is going to give us a mass number of 13. And so if we write a little small here, we should see something like that. Okay, so let's do the second one here. So this is molybdenum, and molybdenum has 42 electrons when it's neutral, and so that means it should have 42 protons as well. And then if we want to figure out how many neutrons we have, we should look over here at our mass number. So our mass number, this is going to be our neutrons and our protons added together, and this should be 54 plus 42 should give us 96. And then finally our atomic number should be equal to our number of protons. And so let's see if I can once again write this kind of small. Let's see, not doing a great job there, but there we go. Okay. Okay, so let's do aluminum 27. So aluminum 27 has a mass number of 27, and it has 13 protons. And so we know, of course, the atomic number is 13. I'm going to switch to a little more finely. There we go. That's much better. So the atomic number is equal to the number of protons. because this is neutral, the number of electrons should cancel with the number of protons, right? They're going to be equal charge. And then we're going to try and figure out from our mass number here how many neutrons we have. And so it's going to be 27 minus the number of protons, which in this case should be 13. And so that should give us a 14 neutrons for this aluminum 27. Okay, last and certainly not least, we have cesium down here. And so cesium, we have the atomic number. An atomic number, it should be equal to our number of protons, 55. And then when we're looking at our mass number, that should be our number of protons plus our number of neutrons. So let's do some fast math here. 78 plus 55, 3, and that's going to be 1 up there. And so that's going to be 133. And that should be 133 cesium and 55 on the bottom. Okay, our last subatomic practice problems. And let's get some practice with removing and gaining electrons. And so let's kind of see how this balances out. Let's figure out how many protons and electrons for each of these ions. And so if we look here, we're talking about each of these are going to be elements. And so K is for potassium. Potassium has 19 protons. And this particular one is a potassium cation, which means that it is missing an electron to make it neutral. It has more positive than it does negative. So if it's missing one electron, then we would say this is an 18. So 18 negative and 19 positive should give us a positive 1 charge. Okay, we have sulfur, and now we have -2. So this is telling us that we have too many negative charges. So if we're trying to generate this -2 charge, we would take 16 positive and 18 negative, and that will give us the -2. And this is going to be a sulfur anion in this particular case. Okay, so we have calcium +2, Ca +2. This is telling us that we have too many positively charged subatomic particles, or too many protons. And so in this case, we look here and we have 20, so we should have 18 corresponding electrons. 18 negative, 20 positive should give us a +2 or a +2 calcium cation. And if we have Br minus, this is telling us that we have one too many negatively charged subatomic particles to make a neutral species. And so if we have 36 electrons, we should only have 35 positively charged protons in our nucleus. 36 negative electrons and 35 positive give us that 1 negative anion of bromide. And then finally, we have aluminum, aluminum with a +3 charge. This is aluminum cation. And this is saying we have 3 too many positively charged protons to have a neutral molecule. And so if we have 13 protons, that means that we should only have 10 negatively charged electrons. So 10 negative and 13 positive should give us a +3 for an aluminum cation.